Hello everyone. I'm another TA here to talk about some advanced topic in flow matching. So let's start with a quick recap of what flow matching does. So flow matching is an algorithm that learns to match one distribution to another. So for example, from a Gaussian distribution to the image manifold. And our goal is to find the velocity field that transports samples from the Gaussian to the image manifold. However, we don't have access to the ground truth velocity field. So to simplify the problem, we can randomly sample a noise vector x0 from the Gaussian and an image x1 from the dataset, and define the ground truth velocity as x1 minus x0. So we want the learned vector field to be as straight as possible, so that we can reduce the integration error when using the Euler method when inference. And as a result, this also help reduce the overall sampling time. But however, in reality, the learned velocity field tends to have high curvature. This happens because of the random coupling between x0 and x1. Here is an example of random coupling. By overlapping these plots, we can obtain this graph. So at each intersection, the model predicts the expected velocity rather than the true velocity. This means the main reason why the learned velocity field exhibits high curvature. To address this coupling problem, a natural alternative is to use optimal transport. I'll provide a brief definition here, but I won't go into details. Anyone interested in the formal definition can pause and review it on their own. So basically, you just need to know that optimal transport field finds a coupling that minimizes the distance function. And by minimizing this distance function, we can obtain a coupling without intersections. So let's solve the problem. But however, calculate optimal transport for the entire Gaussian is computationally expensive. So we can only compute it for a batch of data. And recently, semi-discrete optimal transport has emerged as another approach. You can look it up if you are interested. Next, I will talk about mean flow. The concept is quite simple, and the key question is, can we predict the average velocity field instead of the instantaneous velocity field? Using the average velocity field also significantly reduces the curvature. However, how to derive the average velocity from the instantaneous one is a big question. So next, we'll dive into some of the math behind it. The average velocity is defined as the integral of the instantaneous velocity over a time interval and divided by a length of that interval. Next, we multiply both sides by t minus r. And then we take the derivative with respect to t. And then using the product rule, we can derive this equation. And after that, we subtract the second term from both sides. And at this point, we still don't know the time derivative, but we can derive it using the chain rule. Like this. So the first coefficient equals the instantaneous velocity, and the second coefficient is 0, since r and t are independent. And the third coefficient is clearly 1. By substituting this coefficient, we obtain the desired equation. Unfortunately, this equation is a Jacobian vector product between these two vectors, which can be computed directly using torch.func.jvp. And at this point, we are almost done. Let's summarize the loss term in mean flow. The first term is the predict average velocity field, and the second term is the ground truth average velocity field. The SG here stands for start gradient. So, and when computing the ground truth average velocity field, we use not only the dataset but also the derivative of the average velocity field. Using stop gradient prevent double backpropagation, and in practice you can simply use detach to achieve this. And finally, you only need to replace the instantaneous velocity with the per sample velocity. The last slide shows the pseudocode for mean flow. Note that some variable names differ from those in our slides, so please be careful. And let's call it a day.